Hey, welcome back to Fundamental Physics. In this video, we're going to do more examples of analyzing circuits. So hopefully you checked out the previous video, which is strategies on how to analyze circuits, because now I'm just going to go through examples, apply them, apply Kirchhoff's laws, apply the strategies, and doing my best to explain how I did each step. Starting with example 1 here. Here we have a circuit. If resistor 2, this guy, has a resistance of 4 ohms, and the battery supplies an EMF of 12 volts, find the current through R4. So we need to find this current here, and we want to find the current through R2. Okay. Alright, so notice that here we have a few resistors here in parallel as well as in series. So let's just double check our understanding of current. We know that the current leaving this battery here, this is going to get divvied up, split amongst these two pathways, and then they're going to combine here at this junction, and then it's going to go through this 4th resistor and back to the battery itself, meaning that the total current going through the battery is going to be exactly the same as the current here going through the 4th resistor. But that current is not going to be the same going through this 2nd resistor, because that's going to depend on how this current gets divvied up across each of these pathways, which then of course will depend on the resistors that are in each pathway as well. So let's begin with finding the total current, because that's going to give us our I4. That's going to be the easiest for us to figure out. So let's do that in red, and let's see if I can do it in this space that I have set myself over there. Oh, and guess what? There's a 4th question. What is the power dissipated in R2? That's actually not very hard, because once we know the current through R2 and its resistor, we can then find the power dissipated. So let's begin with finding total current. And based off of that previous video I just talked about, to find the current, total current, we need to simplify our circuit. We need to make it so that it looks like this. Basically, you have a battery and you have one resistor, which is your total equivalent resistance inside your current circuit. That's going to be tricky because we have you have resistors here that are in parallel, and you have them in series. Actually, you have them in series and then parallel and then series. Okay, so one step at a time. I decided to put this question on a new page, otherwise it was going to get really messy. Okay, so remember I said we want to reduce our circuit to something that looks like this. You'll notice that it's going to be a little difficult to do that in one step. So maybe what I want to do, and I'm going to do it on the side over here, is I want to take this big circuit and I want to reduce it down one thing at a time. The first thing I'm going to do is I'm going to have to start to combine resistors one at a time. So here we have these two in series. That's probably the easiest to combine right now. Notice if I try to combine this with these in parallel, it doesn't quite work, because these two resistors are both in parallel with R3, which if we had simplified it so that these two resistors are one combined resistor together, then it would be better to then combine with in parallel with R3. So let's do that first. I'm going to make my circuit look like this, so that we get one resistor here, and then these two resistors on the bottom in series, I will combine them into this total equivalent one here. I'm going to call this R12, because they're just 1, 2 put together. This over here is R3 still, and that's just 5 ohms. This guy over here, R4, is 10 ohms. Okay, we know that for series, resistors in series, we just have to add the resistance. 6 ohms plus 4 ohms is going to be 10 ohms in total. Okay, so that's the first step. We're going to start to slowly combine resistors one at a time. Now this next step, the easiest one to combine now, is to combine R3 with R12. So let's do that next. We know that these two resistors are in parallel. So to combine them in parallel, we got to use the parallel rule, which if I did that, this is going to be R3 plus 1 R2, or just 3 and 3, 1, 2, basically. Actually, I'll just call it 3, 1, 2. This is the combined resistance of those resistors here. R4 is just sitting over here. That's 10 ohms. And I know for these two batteries in parallel, I need to add them this way. 1 over R312 is going to be 1 over R3, which is 5 ohms, plus 1 over R12, that's going to be 1 over 10 ohms. And if I add these together, I'm going to get 1 over R312 equals, this is going to be 2 plus 3, 3 over 10. That's going to be 3 over 10. Did I do the math right? Times 2 times 2, 2 plus 1 is 3, 3 over 10. Okay, which means that R1312 is going to be equal to 10 over 3 ohms. Okay, so this here is 10 over 3 ohms. Okay, we're almost there, because all we have to do now is just combine the last two resistors in series, which we just have to add them. And that resistor, the total resistance, I'm just going to call R total now, because if I combine all the resistors, that's what it would be. So that's 10 over 3 ohms plus 10 ohms. And you know what? I'm just going to put it in my calculator. I get 13.3 repeated. 13.3 repeated ohms. Saving that in my calculator. Okay. We finally got the total equivalent resistance. So the total equivalent resistance here, 13.3 repeated, whoopsies. Which means if I want to find the total current based off of Ohm's law, I will get the Ri total is V divided by R total, 12 volts over 13.3 ohms. That's 0.9. I get 0.9. I get 0.9 amps. Okay, that's important. Now that I know the total current, I know that's going to be the current through R4. And so that's it. I don't have to do any more calculations. I'm done. And hey, look, yay, we got it. Perfect. So we did A. We're done with A. We found the current through R4. Next up, we need to find the current through R2. To find the current through R2, we need to know how this current splits up over here. And we know, even though we know this total equivalent resistance, which is down over here, over here, this is 5 and this is 10, that doesn't quite tell us how the current is going to get split up. Although from a proportional perspective, you may have an idea. You might think that, well, because this current up, this resistance up here is half that of the other path, this pathway is going to get more current, and probably definitely maybe 2 times more of what this other 2 times more current than what this one down here is going to get. So based off that reasoning, you could figure out that if I took 0.9 divvied up into 3 parts, 1 part goes through the bottom, 2 parts goes up the top. Well, you could think of it that way, which yes, it gives you 0.3 amps. But what happens if you don't get perfect numbers to work with? And that's what I want to deal with. If you don't know, or if the numbers don't work very well, you only know the resistance. You only know the resistance going through R3, you only know the resistance here. You don't know the current, you don't know the potential difference even. So in order to get the current, you need 2 out of those 3 things, or power, but we don't have that either. So you probably need to know the potential difference across this, across these resistors. And no, it is not going to be 12 volts because you also have this resistor over here. So that's probably our first step that we have to figure out, is we need to find the potential difference across these resistors, since the potential difference will be the same across R3 and R2 plus R1 combined together. So let's do that first. Since we know, I'll do this question in blue, since we know the total current going through R4, we can use that to find the potential drop across R4. If we know the potential drop across R4, we know how much potential difference is left remaining for the other part of the drop, for this other part, okay? So this is going to be, what is the total? 0.9, oh, that's current times R here. So that's 0.9 amps times the resistance, which is 10 ohms, and that's going to give us 9 volts. Wow, there's 9 volts of drop. That's a big drop there, okay? So since this is a drop of 9 volts, this potential drop must be not 12 minus 9, that's going to be 3 volt potential, 3 volts of potential difference drop across these resistors. To find the current now, we then know, since we know the potential drop here, which is going to be 3 volts, then we can use the 10 ohms, the 10 ohms with the 3 volts to figure out the current. So the current across R2 and 1 is going to be V over R, 3 volts over 10 ohms, and that's going to be 0.3. Repeat it. No, it is 0.3, sorry. 0.3. How many sig figs? 2 sig figs. So 0.3 amps. And the thing about, and you might be thinking, but we use the equivalent resistance. We have to figure out for R2. Well, guess what? Since these resistors were in series, the current across R1 is going to be the same as R2, and is going to be the same across R1 too. It doesn't matter if we combine them or not, the current is going to be the same. So there we go. We found the current for R12 or R2. It doesn't matter. The two combined together. Okay? Alright, so we did B now. Last up we have C. I'll do this one in purple. Okay? Oops. Well, we haven't done it yet. So what is the power dissipated in R2? So for R2, we know many things already. We know the resistance, which is 4 ohms. We also know the current, which is 0.3 amps. Next up, we want to find the power dissipated. So the power dissipated, there's many different equations that you could use for power. Remember, there's I squared R, there's also V squared over R, and there's also V times R, okay? So which one to use? Well then, we just have to be very careful because the V, there's many V's in this question, there's many I's in this question, and many R's. Well, we do know the R has to be specific to the resistance, the resistor. But for the I's and the V's, the I has to be specifically the current across this resistor. The potential difference has to be specifically across that resistor. So it would be wrong to use 3 volts here because the 3 volts is the drop across both resistors, not just R2. So in fact, it would just be more work if I try to figure out the potential difference across R2. I do know the current, I do know the resistance, so why not just use this one? This one over here, I know it's the 0.3 amps, and it's specifically the current going across that resistor. The resistance is 4 ohms, and all I have to do is just put this in my calculator, and we should get 0.36. And since this is power, our answer is in watts. Okay, and that's exactly what is in C over there. Okay, all right, phew, wow, that took longer than I thought. But hopefully, me going through this gave you an idea of some strategies and pitfalls how one might solve analyzing the circuits problem. So thank you for watching, and stay tuned for more of these. Fat Mama Physics signing out.